Okay, tech question here. Let's have a look. The population of Ohio was approximately 500,000. The population increased at 5% a year. Write an exponential function down. Okay, okay, let's do that. So it's by 500,000, 1.05 power t. Use A to determine the rate at which the population increases. Okay, there we go. And use B to determine the rate at which the population increases in 10 years. Okay, 10 years. There we go. Okay. An isotope of the element herbarium has a half-life of approximately 12 hours. Initially, there's 9 grams of it. Write an exponential function that relates to the amount of substance remaining after t hours. Okay, so starts off with 9 grams, but then it halves every 12 hours. I guess the formula would be like this. So when you'd multiply it by a half after 12, I think that would be it. Let me just plot it. Yeah, that looks right. Okay. Use uh, use A to determine the rate at which it's decaying in t. Okay, so that's the derivative. And then after 4 hours. Okay, there we go. Where are we now? Okay, 361. The number of cases of influenza at the beginning of 1960 to the beginning of 1961 is modeled by this function, where nt is given the number of cases in thousands and t measured in years, with t equals 0 at the beginning of 1960. Okay, so nt 5.3 exponential 0.093 t squared minus 0.87 t. Okay, calculate n0 and n4. Okay. Okay. Right. Okay. So this is just the rate per year in thousands that influenza cases are growing. Is it? No, this is how many cases there are. So decreasing. 5.3 and 0.7. Interesting. Calculate the derivative at 0 and 3. I wonder why they didn't go with 0 and 4. That would have made more sense, right? Okay. And then sub in 3. Both negative. It's not surprising. Declining. I want to graph this. Yeah, it's declining. Yeah, and that's why it's negative. Okay, that's fine. It's the rate at which influenza cases are decreasing per year at 0 and 3 years. Leveling out here at about, well, actually, if I zoom out, it increases again, which I think this equation maybe isn't accurate too far into the future. Okay, let's have a look. Next one. The relative rate of change of a differential function is given by that. One model for population growth is the Gompertz growth function given by that. Okay, so let me type this in. A exponential minus b and exponential again minus cx. Okay. Find the relative rate of change formula for this. Okay, so we'll have to calculate the derivative. And then it's that over that times 100. So line 28 over line 26 times 100. Okay, oh, that's a nice formula. Use A to find the relative rate of change. X is 20. Okay, sub in X is 20. A is 204. Hey, where did my A go? A has disappeared? Where did my A go? Oh, it cancelled away. Funny. 0.0198 for B. 0.0198. And then 0.15. Okay. Okay. And briefly interpret the result. So this means that the rate of change as a percentage of the population size is not even 1%. Oh. We got answers here we can check. Okay, let's see. Okay, what have I got here? I can check first. The 5% thing. No, that's the next one here. Well, let me check. Let me check the last one if I can. Minus 0. Oh, this must be an even one. Check the previous one. Yeah, that's right. That's a pity. I can't check. I want to check this one. It's a real pity. Okay. Okay. Yeah. Oh, this is an Excel question now. So maybe that'd be a good point to leave the video there. Okay.